In this video, we're going to derive, to order of magnitude, the interaction of radiation and matter, mostly based off of a simple model of a hydrogen atom as a proton with an electron going around it. This kind of simple model is sometimes called the Bohr atom, after Niels Bohr. Now, it'd be nice to do this derivation using only things we know from classical physics, like the electric force and angular momentum and things like that. And mostly we'll stick to that. But to really capture the more interesting behavior of these atoms, it's going to be necessary to introduce a little bit of quantum physics. So we'll call this a semi-classical derivation. So the little bit of quantum physics that we're going to have to inject at the beginning of this derivation is we need angular momentum to come in quanta. That is, we can't put an electron with an arbitrary angular momentum around this proton. It has to come in specific increments. So suppose our electron is going around with velocity v sub e, for velocity of electron, and is a distance a sub 0 from the proton. Then quantizing angular momentum gives us that the mass of the electron, m sub e, times the velocity of the electron, v sub e, times the radius, a sub 0, so this is the angular momentum, has to come in units of h bar. So we'll say n units of h bar, where n can be 1, 2, however many units that we want. So this is a quantum mechanical result that angular momentum has to come in quanta. But after injecting this, we can do a surprising amount just with classical derivation. So even though quantum mechanically we know that this electron doesn't actually spin around this proton, it occupies a cloud of probability space around the proton, we can pretend that it is just a little particle running around and around this proton. This is our classical derivation. And if that were the case, we can balance the force required to keep this electron in a circular orbit around the proton against the electric force that's holding the electron close to the proton. And those forces need to be equal. So the acceleration required to keep something in a circular orbit at some velocity is equal to v squared, in this case we're talking about the velocity of the electron, v sub e, over the radius, which in this case is a sub 0. So that's the acceleration keeping this electron in circular orbit. The force is then just the mass of the electron times that. And we want to balance that against the electric force pulling that electron towards the proton, which comes in units of the electric charge squared, the product of the electric charge of the electron times the electric charge of the proton. And that force falls off as r squared, which is a sub 0 squared. And we'd like to make this kind of a general derivation. So I'm going to put a number z out here, where z is the charge of the nucleus. So we're doing a derivation of a hydrogen atom with just one proton in here. But one could also imagine doing this derivation for a helium atom that's been ionized once. So it's a helium atom with two charges, two protons in the center, but still only one electron going around it. Or you could do lithium that's been twice ionized. So again, now there'd be three charges in the center, but still that one electron. So this Z is a way of extrapolating our hydrogen atom to other single electron atoms that may not be completely neutral. Now let's remember that the velocity of the electron, giving our equation up above here, is equal to n h bar over the mass of the electron times the radius. And we can plug that into this equation here for n equals 1 to get mass of the electron, Planck constant squared, over the mass of the electron squared, over the radius, and there's an a squared here, and there's another a here, so it's a cubed. It's going to be equal to z e squared over a 0 squared. So solving for a, we get h bar squared over the mass of the electron divided by e squared divided by z divided by e squared. And numerically that comes out to be just about half an angstrom, so 0.52 angstroms, and it scales inversely with z. So the more charge you put into the center of your atom, the closer the electron orbits. But for a hydrogen atom where z equals 1, the radius is about half an angstrom, and that's called the Bohr radius. What we can do with this Bohr radius is ask how much energy is required to ionize this atom, which is to say, how much energy does it take to get this electron completely separated off to infinity from this proton. And this energy is often called a Rydberg. we can compute this just as the potential energy of the electric field for this electron sitting at radius A0. Because whatever the potential energy is of the electron at that point, we have to pay all of that energy in to get this electron completely out of there. But as we know from electrostatics, the potential field scales as the charge squared over radius r. And I'll toss in again our z. So it's the product of the charge in the nucleus, which is z times e, with the charge of the electron, which is e, at radius a0. This is the potential energy of the electron orbiting at that radius. Now in a classical derivation, that'd be all there is to it, but we're going to fudge things a little bit to get them to correspond to a reality. And to fudge them, I'm going to throw in an extra 2 here. So we've deviated slightly from our classical derivation, but it's okay, this is just a semi-classical derivation. So if we actually plug in for what A0 is and do our math, we end up with z squared e to the 4th, it's the mass of the electron, over 2 h bar squared. And numerically, that comes out to 13.6 electron volts. And we'll go ahead and keep our z dependence here with a z squared. So for hydrogen, where z is 1, it takes 13.6 electron volts to ionize it. And that's something worth remembering. 13.6 electron volts is up in the ultraviolet range of the spectrum, and the process of absorbing a photon to ionize an atom is called photoionization. So this is the energy required to photoionize hydrogen from its ground state. It's a Rydberg. Now one other thing that might have been nice to do here is to look at the energy difference between two different electronic states, two different n's here, for n being our increments of angular momentum. So let's examine the n equals 1 to n equals 2 transition. Now remember when we were deriving the velocity of our electron, it was basically proportional to n. And we plugged in for v squared here, looking at the force required to keep this electron in circular orbit. So everywhere we see an h bar, we need to put in an n. So there was an n squared because we had an h bar squared. The radius of an electron orbiting at some angular momentum state here is proportional to n squared. And so the Rydberg, when we start talking about the energy between two different states here, this is the energy required to photoionize an atom from the nth electronic state. So if I am trying to go from energy state 1 to energy state 2, and I know how much energy it requires to photoionize from energy state 2 and to photoionize from energy state 1, I can just subtract these two to get the energy to go from 1 to 2. So I'm going to take the energy of the 1 to 2 transition, that's just a Rydberg, which I'll call RYD here, which is this energy evaluated for n equals 1, times the n equals 1 state, minus the n equals 2 state. So if we're going from state 1 to state 2, we plug in 1 for n1 and 2 for n2. So that's 1 minus a quarter equals 3/4. So this would tell us that the first electronic excitation in a hydrogen atom should be about 3/4 of a Rydberg, which comes out to be 10.2 z squared electron volts. Now in hydrogen, this first electronic excitation, the 1 to 2 state, is called the Lyman alpha transition, and sometimes abbreviated Ly alpha. So a Rydberg was the energy required to completely ionize hydrogen, or a hydrogen-like atom, from its ground state. Lyman alpha is the energy required to do the first electronic excitation. And this basically gives you the scale of the energies involved in the electronic transitions. Now as you go higher and higher up this ladder, you can difference the second state with the third state. You could difference the first state with the third state if you wanted to. But because this is quadratic, these energy states get closer and closer together as you go higher and higher up the ladder. So even though Lyman alpha, the first electronic transition, is still firmly ultraviolet, by the time you get up into the range of n being something like 200, the energy difference between adjacent states is very firmly in the radio band. It can be something like a gigahertz. So the energies of electronic transitions start in ultraviolet. They can rather rapidly drop down into the optical range and into the infrared, and even end up eventually into radio. So it's very hard to put a hydrogen atom into an excitation state that's so high that the energy difference between the state it's in and the electron being completely free of the proton is so small that the corresponding wavelength is in the radio band. These higher energy states are important and do get emitted often when protons and electrons capture one another. That is, as a electron comes sailing in from infinity and gets captured by this proton, you can often get a cascade through these various energy states and emit a whole bunch of radio emission, which are called radio recombination lines, on their way down into these larger increments where it starts emitting optical and then ultraviolet photons as the electron cascades down into a ground state. So that's an order of magnitude derivation of the energies involved in electronic transitions. The next level down, which might be useful to look at, are the energy levels involved in fine structure transitions. So what are fine structure transitions? Well, the fine structure interactions happen because this electron has a magnetic moment, which we'll call mu, originating from the fact that this is a charged particle that has a spin, and that creates a magnetic moment. And the other key component of a fine structure transition is the fact that as this electron is spinning around this proton, it sees a magnetic field from the proton. Now, this magnetic field for fine structure isn't the spin of the proton. That's called hyperfine. It's the fact that from the electron's perspective, this proton is spinning around it, and a charge moving in a circular orbit induces a magnetic field. Said another way, the electric field of this proton, the Coulomb field, in the frame of reference of the electron, Lorentz transforms into a magnetic field. So for fine structure transitions, the energy of the transition is basically related to the interaction of that magnetic moment of the electron with the magnetic field that comes from the electron and the proton moving with respect to one another. And in general, these are vectors. They point in a direction, and the energy difference is going to be comparable to the dot product of those. So we'll see if we can estimate these two terms. First, let's try to estimate B. And we'll drop the vector here because we're just trying to get a sense for the magnitude of B. Well, we know B is resulting from a Lorentz transformation on the electric field. So the electric field of that proton had to do with however many protons we had in there, Z, times that many units of charge, E, over the distance that we are from that proton, which is a Bohr radius, A sub 0, squared. So that's the electric field. And then how much of that gets coupled into your magnetic field, appears as a magnetic field, is the ratio of the velocity, which is dominated by the velocity difference, which is dominated by the velocity of the electron, compared to the speed of light. How do we estimate that? Well, we had previously, by quantizing our angular momentum, that the velocity of the electron was about h bar over the mass of the electron times the radius. And we'd also solve for the Bohr radius with A0 being h bar squared over the mass of the electron, the electric charge squared, times z. So if we plug A0 into here, the Bohr radius into the velocity equation, we get that the velocity of the electron compared to the speed of the light is about the charge squared. The ME's cancel out. One of the h bars cancel out. So we get an h bar, and then we get this factor of c over here. And this is what is called the fine structure constant, which is called alpha. And to an excellent approximation, the fine structure constant is equal to 1 over 137. So that's the fine structure constant. If we plug that in for B, and I should have propagated a z through here, but to avoid distracting from the fine structure constant, which is really for hydrogen, I'll just go ahead and put it into B here. We plug that in, and we end up with B being of order z times e cubed over h bar c times the Bohr radius squared. So we have one of the factors contributing to the energy levels of the fine structure transitions. The other is we need to estimate mu, which, if you remember, was the dipole moment of the electron. So to do that, we'll do things slightly backward. The magnetic field of a dipole generally goes as the magnetic field, but it drops off as r cubed. So flipped around, we could express the magnetic moment of the electron as being the magnetic field from the electron evaluated at the radius of the electron times the radius of the electron cubed, where Re, when I say radius of the electron, I don't mean of its orbit, I mean the classical radius of the particle, the electron. So how the heck do we estimate the radius of an electron? Well, take all the energy bundled up in your electron, which is the mass of the electron, times c squared. That's E equals mc squared. And you set that to the potential energy in the electric field. You're basically saying, take all the energy in the electric field that comes from an electron, and that is what's giving rise to the mass of the electron. And that is E squared over the radius of the electron. So classical radius of an electron is E squared over me c squared. So now we invoke Maxwell's equations and say that the thing that causes a curl in a magnetic field is a current, 4 pi over c times a current, which is usually labeled a J. So if we roughly call this curl in the B field to be the magnetic field of the electron evaluated all around the exterior of that electron. So we basically just walked around the outside of this electron and divided the magnetic field across that whole circumference. We can set that equal to 4 pi over c times some current associated with this electron spinning around, divided by the surface area of this electron, which was 4 pi radius of the electron squared. So we took the current density here and we estimated it as the charge of the electron spinning to create a charge flowing around the surface of this electron. So this sounds a little hand-wavy, but I promise it's going to be useful. The last thing we really need to estimate here is I, this current. And we say that current is really, it's about the charge of the electron divided by, so current is charge per time, so we're dividing that by some time scale. And I'm going to select the time scale of the electron spinning around, so t spin. And how do we estimate t spin? Well, just like we quantized the angular momentum of this entire atom, we could quantize the angular momentum of an electron to say that h bar is equal to mass of the electron at the radius of the electron squared times the angular frequency of the electron spinning, which is 2 pi over t spin. So I won't get into all the messy algebra, plugging everything back in. The t spin that we solve for here by quantizing the angular momentum of the electron spinning, plugging into the current, which we plug in to solve for the magnetic field of the electron evaluated at the surface of the electron, which we then use to estimate the dipole moment of the electron. We'll plug that all back in and you end up the magnetic moment of the electron being E h bar over 2 times the mass of the electron times c. So we have the magnetic moment of the electron here, and we have the magnetic field that arises from the electric field here seen through the lens of a moving frame of reference. And I should mention before I move on here that you can use the same kind of estimation that we used for estimating the magnetic moment of the electron to estimate the magnetic moment of the nucleus. You end up with mu p as being the charge of the nucleus, Ce times h bar over 2 times the mass of the proton times c. So we've just substituted Ze for E here and the mass of the proton for the mass of the electron. And this is the general form of what's called the Bohr magneton. All right, so I'll clean up a little here. So we get back to delta E, the energy of fine structure transitions is going to be about the magnetic moment of the electron times magnetic field. We just plug in here, we have E h bar for 2 times the mass of the electron times c, and that's multiplied by the charge of the nucleus interacting with the Lorentz transformation, get an E cubed over h bar times c times the Bohr radius squared. So we multiply this all out, and don't forget that inside the Bohr radius are some z's. You end up with something that scales with the charge of the nucleus to the 4th power times the fine structure constant squared. Remember, this is the fine structure constant over here, times Rydberg. So fine transitions in general are a factor of alpha squared smaller than electronic transitions. And alpha is about 1 over 137. So that means fine structure transitions are roughly 10,000 times weaker than electronic transitions, which is why they're fine structure. It's small compared to the electronic structure. So those are the energies of fine structure transitions. And if you don't want to remember all of this business about magnetic moments and Lorentz transform fields, the important thing to keep in mind is that you have a fine structure constant, alpha, and energy scale is alpha squared. So the last kind of transition we need to think about when we're talking about an atom is hyperfine. And as I already alluded to earlier, this is the interaction of the magnetic moment of the electron here with the magnetic moment of the nucleus. And just to be clear, this magnetic moment is arising from the spin of the nucleus. So the B field now, we're still dealing with an energy difference that is the product of the dipole moment of the electron times a B field. But in this case, the B field is the field of the dipole moment of the Bohr magneton at a distance of the Bohr radius. And you remember that dipole fields fall off as distance cubed. And it turns out that this B field is about the magnitude of the B field we just calculated for the fine structure times the ratio of the mass of the electron to the mass of a proton. So consequently, the energy difference for a hyperfine structure is going to be about the energy difference for fine structure times this ratio of the electron mass to the proton mass. And this factor, as you almost certainly appreciate, is about a factor of 1 over 1,000. So hyperfine transitions are about 1,000th the strength of fine structure transitions. So this is great. We've gone with a semi-classical derivation of the Bohr atom and derived, to order of magnitude, the energies of the electronic fine structure and hyperfine structure transitions. The last thing that we might do in order to just round out this discussion of radiation and matter going beyond single atoms to maybe talk about molecules or to talk about the vibrational and rotational transitions in molecules. So the picture we want to have here now for molecules is that of a dumbbell where we have two atoms attached by maybe a spring. And we can talk about vibrating these atoms with respect to one another, the vibrational transitions where they move toward each other and away from each other, versus rotational transitions where they circle around each other. So for vibrational transitions, the energies of molecular transitions just follow the characteristic harmonic series for a harmonic oscillator, which if you're fresh on your quantum mechanics of harmonic oscillators, you'll remember the nth energy state being given by n plus a half times h bar omega, where omega is the characteristic frequency of the harmonic oscillator and is generally given by, if this were a spring, square root of k over m, where k is the spring coefficient, where the force is given by k times the displacement from equilibrium, x. So if we're trying to do this to order of magnitude, we could say that what is this displacement? Well, it's probably going to be about the scale of a Bohr radius. And what is this force? Well, it's the electric force given by E squared over Bohr radius squared. So if you solve for K here and you plug in, say, the mass of the proton here, this is basically assuming we have hydrogen atoms. So this is like an H2 molecule. Plug this in for K, plug this in for omega, you end up with the energies of these transitions for vibrational being of order a Rydberg times square root of the mass of the electron over the atomic mass times the mass of the proton. So this is keeping track of the fact that we may have, say, a neutrons along with our protons in the center of our atoms, and that slows down the oscillation. And as you can see here, in the best case of the lightest atoms you can have, with A of being essentially 1, the energies of these transitions are certainly lower than electronic transitions. But if you remember that the fine structure transitions had a alpha squared factor in them, so they were 1/10,000th of a Rydberg, these are typically going to be something like a 30th of a Rydberg for light atoms like hydrogen, and energies will go down from there. Now for rotational transitions, the big thing to remember, as always, is that angular momentum comes in units of h bar. So that means the moment of inertia of your molecule times your angular frequency comes in units of nh bar. The energy of the nth state is going to be 1/2 I squared. So plugging the quantized angular momentum in for the energy, we get 1/2 n squared h bar squared over I. And if we recall that the moment of inertia, we assume, let's say, a symmetric molecule, the moment of inertia is the sum of masses times the square of their distance away. Then if we assume separations are of order Bohr radius, we end up with 2 times the atomic mass counting for each molecule, each of which is at a distance a0 over 2. Then we end up with a times the mass of the proton, so that's the molecular mass over 2, so Bohr radius squared. So plugging this in over here, we get that the nth energy state is of order n squared h bar squared atomic mass times Bohr radius squared. And the interesting thing is these rotational transitions only lightly depend on the electric force, only insofar as it sets how far these molecules are apart from one another. And one thing I should mention on rotational transitions before we finish with them is that it can be very confusing to use these letters N to label the states when we use N to also mean the electronic states. So typically, when we're talking about molecules, we'll use a J there instead of N. So you'll talk about the energy of the jth rotational state. And these go as J squared h bar squared over the atomic mass and the Bohr radius squared. And it's worth noting that the steps in energy levels for rotational transitions for a typical molecule is about 2 orders of magnitude smaller than the energies of vibrational transitions. So rotational transitions are lower energy. So that's it. To order of magnitude, we derive the energy levels and therefore the interaction with photons for atoms and molecules, ranging for electronic transitions, fine structure transitions, hyperfine transitions, and then for molecules, vibrational and rotational transitions.